You're welcome to my YouTube channel. So today I will continue from where I stopped in my last video on cumulant generating function. So a recap, in my last video, I explained that the cumulant generating function, we can use kxt to represent it, is the log E of the moment generating function. I also said that the moment generating function, we know it is expected value of E T X. Similarly, I explained the first cumulant. So let me use K1 to represent the first cumulant. I said the first cumulant is expected value of X. I explained that the second cumulant, that's after if you differentiate the cumulant generating function once, you get the first cumulant and it is expected value of X. If you differentiate the cumulant generating function 2 times, you will get the second moment about its mean, which is similar to expected value of X minus expected value of X all square. If you differentiate the cumulant generating function the 3rd time, and when you after differentiating, you have to equate t to 0. So if you differentiate it the 3rd time and equate t to 0, you will get the 3rd moment about its mean, which is similar to expected value of X minus expected value of X all raised to power 3. If you differentiate the 4th time, you will get the 4th moment about its mean minus 3 times the 2nd moment about its mean all square. And this is equivalent to X minus expected value of X all raised to power 4. So this is for the 4th moment about its mean, then 3 times expected value of X minus expected value of X. So all these are all raised to power 2, which is the 2nd moment about its mean. Then all these all square. So that's it. Then I also give an example. I solved an example in my last video for normal distribution. So in this video, I will solve for the Poisson distribution. We know that the MGF of a Poisson distribution is exponent lambda E raised to power t minus 1. So this is the MGF of a Poisson distribution. And X follows a Poisson with parameter lambda. To get the cumulant generating function of a Poisson, first, remember I told you, you have to get the MGF. Okay, let me just solve for the MGF first. The MGF of a Poisson distribution. So let me not assume. Let's get the MGF of a normal distribution. So the MGF of a normal distribution, which is MXT, expected value of E T X. Remember X. Remember f of X. F of X, Poisson, is e raised to power minus lambda X over X factorial, where X is going from 0, 1, 2, down to infinity. And lambda is greater than 0. So the MGF of a Poisson distribution, which is the expected value of ETX, will be summation. X is going from 0 to infinity ET X times f of X. This will give me summation X from 0 to infinity ETX. What is the f of X? E raised to power minus lambda X over X factorial. Look at this. I'm summing with respect to X. So since I'm summing with respect to X, I can take all the constants outside. Constant means all the objects or all the functions that do not have X attached to it. So look at this, there's no X attached to it. So I can take it outside because it's not a function of X. So this can give me, this will give me e raised to power minus lambda. I'm taking it outside because it doesn't have x, and I'm summing with respect to x. So etx times lambda x over x factorial. If you look at what I have here, the power x is common, so I can factor it out. If I factor x because it is common, I will have e t times lambda factor x out. Both of them have x all over x factorial. I want to do, so let me recall. What is e raised to power 5? So e raised to power 5 means summation from x 0 to infinity 5 raised to power x over x factorial. What is e raised to power 10? E raised to power 10 is summation x going from 0 to infinity 10 raised to power x all over x factorial. What is e raised to power sine x or sine y? Let me use y. It means summation from x going to from 0 to infinity sine y all raised to power x over x factorial. So from all I've written so far, what can you deduce? It means whenever you see summation, this index must not be x, it can be anything. So let me use I. So the index can be I. And we have an object which can be anything. So I can use A now. And this A is raised to power this index. The index we have here all over the index factorial. So looking at this index must be what we have here and must be what we have here. If all these are achieved, then this can be written as e raised to power a. So this is how to expand the power series expansion of the exponent function. If we apply all this, we can get the MGF of a Poisson distribution. Now let's go back to what we have. So we have, let me rewrite what we have there. We have e raised to power minus lambda summation x 0 to infinity. Then we have et raised to power lambda x over x factorial. So looking at this, it looks like what we've been doing so far. So it means whenever you have summation from 0 to infinity of the index, and you have an object raised to power the index all over index factorial, you can write it as the exponent of whatsoever that is there. So you can write it as the exponent of whatsoever that is there. And in this case, we have e raised to power t times lambda. So this becomes e raised to power t times lambda, which is equal to, from law of indices minus lambda, et lambda. So what did I write here before? Okay, so if you factor out lambda, so this is the same thing that I can write it as lambda et minus lambda. So if you factor out lambda, what will you get? Et will remain. What will remain in the second function? 1. So this is the MGF of a Poisson distribution. So if we want to get the cumulant of the Poisson distribution, we'll take the log E of the moment generating function, which is log E of E lambda et minus 1. Recall, log 10, 10, 2 means then log 10 will cancel out the base 10 and I'll be left with 2. Log 8, 8, 5 will give me 5. So follow this, what we have there. Log E will cancel out E. So I'll be left with lambda et minus 1. So therefore, the cumulant generating function of a Poisson distribution is lambda et minus 1. Let's get the first cumulant. To get the first cumulant, you will differentiate the cumulant generating function once. Let me expand this. This will give me lambda et minus lambda. So if I differentiate the cumulant generating function once with respect to t, I will get lambda et. If I differentiate minus lambda, I'll get minus 0. So which is lambda et. To get the value of the first cumulant, you equate t to 0 after differentiating. So that means I have lambda et, I will equate t to 0. This will give me lambda e raised to power 0, which is anything raised to power 0 is 1. So lambda 1 times lambda. Remember, I said the first cumulant, after differentiating the first cumulant, which we called K1, is expected value of x. So therefore, the expected value of x of a Poisson distribution is lambda. Can we get the second cumulant? Yes, we can do that. So to get the second cumulant, you differentiate the cumulant generating function 2 times. If you differentiate the cumulant generating function 2 times, that means differentiate the, look, this is what I mean. So after differentiating the first time, this is what we got. We got this. So that we have to differentiate the result we got after differentiating the first time, differentiate it again. So that's what I mean. So let's differentiate. That means we differentiate the cumulant generating function 2 times with respect to t 2 times. The first time we differentiated, we got lambda et. So it means we are going to differentiate lambda et again with respect to t. So that's what I mean. So if we differentiate lambda et with respect to t, we will still get lambda et. Let me do a recall. How do you differentiate exponents? Remember, recall, if you have e raised to power 5x and you want to differentiate it, the first thing you do, you write everything that is how this law applies to exponent. You write everything and you differentiate the power. If you differentiate 5x, you get 5. So the final answer is 5e 5x. If you ask to differentiate e sine x, so the first step, you write everything. Then you differentiate the power. If you differentiate the power, if you differentiate sine x, you will get cos x. So the final answer is cos x times e sine x. Let's try one more. If you have e raised to power x squared and you are asked to differentiate it. So remember the first step, you write everything and you differentiate the power. If you differentiate x squared, you will get 2x. So the final answer is 2x e raised to power x squared. So applying the same principle, that's what I used to differentiate lambda et. So if you differentiate lambda et, you write et, differentiate t, you get 1. So which is lambda et. To get the value of the second cumulant, we equate about t to 0. So this means lambda e raised to power t equate t to 0. So this will give me lambda e raised to power 0. Anything raised to power 0 is 1, which is lambda. And remember, the second derivative of the cumulant function will give you the second cumulant, and the second cumulant is equal to the variance of x, which is the second moment about its mean, which is the expected value of x minus expected value of x all squared. And after solving, the variance is lambda. So it means the mean of a Poisson is lambda, the variance of a Poisson is lambda. If you try to get, let's try to get the third. Okay, we can stop here. So thank you. Don't forget to like this video, subscribe to this YouTube channel. I will make more videos to explain other part of this topic. So subscribe to this YouTube channel. If you have any topic you want me to teach, you can say that on the comment section. I love you all. God bless you. Bye.